Kaushika sir,
Yes, sir. Yes, sir. Start, Mani, sir.
shall I proceed with welcome?
Yes, sir. You proceed with welcome. Sir. Yes.
Good evening to all. I think today we are here to listen to one of the most known name in the field of civil engineering, that too the concrete for the future. It is about geopolymers, and uh, none other than Dr. N.P. Rajmane sir. Sir, on behalf of ICI Center Mangalore chapter as well as QCrete Readymix RMC Private Limited, we welcome you to this webinar, sir.
Yeah.
And yeah, yes, sir.
Good evening. On behalf of QCrete Readymix Concrete India Private Limited, myself Kaushik, just take a few minutes to introduce Dr. N.P. Rajmane, sir. Dr. N.P. Rajmane, sir, is known throughout India for being one of the persons who have worked continuously on geopolymer concrete. Most of the civil engineers, practicing engineers know him, but it is my job just to introduce him. He did his BE Civil Engineering from BVB College of Engineering. Then he finished MTech in the Institute of Technology, Indian Institute of Technology, Madras. Then he went on to do PhD thesis, of course, in his favorite subject, geopolymer concrete. And Dr. Rajmane sir was founder and head center of advanced concrete research in SRM Institute from 2010 to 2020. And then he was also founder head advanced material lab in CSER Structural Engineering Research Center, Chennai, between 1973 to 2010. And he has traveled extensively throughout the world to talk about, speak about, give webinars, seminars in different parts of the world, from USA to Malaysia to China, everywhere. And then he has been principal member of many committees of Bureau of Indian Standards. He has done extensive work, huge amount of work in fly ash, GGBS, microsilica, and all kinds of SCMs, and probably he was pioneers to achieve long back a 125 MPa concrete as early as in 1980s, and then he has mind-blowing number of technical contributions. More than 500 papers have been published, and then he has been awarded first prize for his paper on low-cost house built with laterite blocks. Again, he got Brij Mohan Lal Memorial Prize from Indian Institute of Engineers in 2005, first prize for his paper on studies on geopolymer mortars using fly ash and blast furnace slag. Then he was awarded Outstanding Concrete Technologist in 2008. And then in 2014, he has been given silver medal for his paper. Again, another best paper award in 2014. The list is very, very big, and probably it will take a long time to read his achievements. And as we said earlier, he has been recognized throughout India. Whoever talks on geopolymer concrete in India, they take Dr. Rajmane's name first, actually. And the today's topic, just 2 minutes I will take. A structure like pyramids have been built with more than 3 lakh blocks. Each of the blocks is said to weigh between 2 to 75 tons. And people like Charles Berlitz has extensively dealt with such subjects on mysteries of the pyramids, and so many books have been written, so many people have done PhDs, and the astounding and stunning theory was given by Professor David Ovitz where he said that the concrete blocks, the pyramid blocks, at least some of them are made by um, synthetic procedures or by human beings using an ancient technology, and it is not natural, at least some of the blocks. That's what he proposed this theory. This is a extraordinary and stunning theory. So if we travel to Egypt, we see a lot of these things actually, which are really amazing. So say for example, apart from pyramids, some of the granite blocks which are weighing more than 100 tons have been placed at about 200 to 300 feet below, and some statues weigh more than 100 tons, 200 tons have been kept below the earth, maybe 300 feet, 400 feet at such depths actually. So these remind us of some extraordinary technologies, and Professor David Ovids proposed this theory of these being made by human beings, that is, the blocks being manufactured by human beings and not natural. And in this regard, we have requested Dr. Rajmane to speak on this, and he accepted our invitation. We are thankful to you, sir, and we are thankful to you on behalf of QCrete and also Indian Concrete Institute. Thank you. This is now the floor is for you, sir. Thank you.
Thank you, Mr. Kaushik. It is an opportunity for me to share my views on this new material called geopolymer. And I had a chance to meet Professor David Ovids also 2 times. Once he came to India, and he was doing his presentations in Annamalai University. At that time, I had just joined SRM University. Then after joining SRM University, after 5 years of my work in SRM University, I had a chance to meet him in France in his laboratory, and he presented his book to me on geopolymer concrete, and I was made to present our work on geopolymer concrete. To tell him that we never used high temperature for curing, used only room temperature for curing, which was not common earlier. Okay, and the pioneering person in this field is actually B.V. Rangan from Australia, and many people referred his work and do the work, and his work was related to actually high temperature curing even before demolding. Anyhow, this is a new material, but this material is not as a competition to Portland cement at all. That let us be very clear. It is not a competition. It is an additional material which has got better actually carbon footprint. In the sense, our carbon footprint means that embodied energy, carbon dioxide emission levels are reduced if we use the geopolymer concrete. So that is our contribution to greenhouse gases which are emerging so much, creating climatic problems in the world. So that's why this material should be viewed in that view. That's why we must not talk much about the cost of this material at all. We must avoid comparing this with ordinary concrete for the cost, though it is not very costly and it may be sometimes cheaper also. Now the cement cost is going up, it may be cheaper also. But I want to tell the audience that let us not consider this as a competition to Portland cement concrete. And also one statement I want to make it very clear here, that whatever we do with Portland cement, whatever we do, it can be made a geopolymer concrete. That means we should not have question how much is the strength, whether we can use in coastal region, whether we can road, nothing. Wherever you are using Portland cement, at that point we can use geopolymer concrete. So it is a full, you can say, utility of polymer concrete in the place of Portland cement wherever it is used. So this is the most important statement, and nobody should have any apprehension. Only thing, the working methods may be different from this to that. That's all. So I wish to introduce first geopolymer concrete little bit for the audience who are not yet aware of this new material, and then I will go to the points I have collected. Actually speaking, Kaushik has made so much of summary of the already being No, I mean, what I want to tell, he had done a wonderful review of the fact that pyramids are made in artificially made stones, not the natural stones. And so that way, as a reinforcement to him. So let us see. And why do you want this lecture? It is only to see that when you make a natural stone artificially, a natural stone looking like stone artificially, still it is good because the chemical nature of what we made in India or geopolymer concrete is similar to that is there in the pyramids. That is actually the first thing we wanted to just show to the people. So geopolymer concrete should not be discussed in terms of the durability because it is already proved to be durable in pyramids. Only thing, formulations we have to do it properly using the presently available materials. That's what I wanted to give the points here. And and this new binder is having this SiO2 L2O3. Okay, wherever these materials are available, we can use that source material. For example, metakaolin. This is a clay-based mineral, and the black manna slag powder, which is hello, hello, not audible, huh? Okay. Am I audible now?
Yes, sir. Yes, sir.
Yes, sir. You are audible.
Hello, audible? Okay, okay.
Yes, sir. Please go ahead.
Okay. Now I wanted to mention that wherever these two chemical compositions are there, oxides are present, we can use it to actually create a geopolymer binder. That means, right now we are working only on these two materials because we are familiar with these two. But it is not because only civil engineers are working in this field in India. That's why we are working with these two. But actually, if other people start working, like chemistry and chemical engineers, we know these are available in so many other materials in the world. I mean, for example, ore waste. So many mines are there, so many ores are there, they contain these two materials. So they can be activated. Okay, and also, so this is not only these two. So India only these two are worked. So I wanted to mention that wherever so that means we can go beyond this fly ash and blast furnace slag, go to the actually the mineral wastes. Okay, and we can start doing it. And it is a polymeric chain. That's why it is having different properties than ordinary concrete. Okay, polymer formation is a different phenomena than the hydration. So let us be clear about it. Okay, and because of this polymeric chain, we have not got any problems with the structural grade obtaining in the geopolymer concrete. We can obtain structural grades even up to M200. There is no problem. We can make it as low as M5 also, even though it is polymer. So it is question of formulations. So formulation will determine the property of the concrete. Okay. Now, is a polymer generally. Polymer is an organic material which is having carbon to carbon actually the bonding. Carbon is connected to another carbon directly. Okay, this is the organic plastics. Okay. Now, when this joining is in many ways, many lines, so many carbons come together, we get the polymer. Okay, this is the basic of polymer. That means any molecule which joins with another molecule. So when many molecules are present in a big molecule, it is called polymer. But plastic and polymer does not mean only carbon. It is a technical word in chemistry, polymer. But now we are applying it to the not carbon. We are applying it to the silicon and the aluminum oxide. So carbon is not present here as a plastic making, polymer making material, silicon element and aluminum element. Again, they should be in this format. It should be surrounded by oxygen. It should be surrounded by oxygen here, Al. Then only we'll get organic, inorganic polymer. Don't think that I am talking too much of chemistry. This is fundamental. Okay, so this kind of molecules have to be generated in our chemical reaction. We need not test for them, but already it is known. But I want to make it clear that these are the molecules present in our geopolymers, which form the silicon and aluminum. There is a silicon here, there is a silicon here, there is aluminum here, there is a silicon. But please note that silicon is not directly connected to the another silicon, not directly connected to the aluminum. It is connected through only oxygen, because that is a 4 coordination point. Because I said these are the 4 coordinates. The 4 coordinated SiO4 and Al2O3 only will become the molecules, bigger molecules. That's why even though there is aluminum silicon, they will never connected themselves directly. They connected through oxygen. Okay, this is the, that's why we get the actually the geopolymer, and that's why we get the inorganic polymer, because this kind of aluminum to aluminum or silicon to silicon binding is impossible. Okay, that is some rule is there called Lowenstein rule, but let us not discuss what is our rule. That is because of the energy level and the chemical nature of the elements we are talking. Okay, now we can see here, this is the original polymeric silica. Okay, silicon, 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 silicon. This is all present in the original mixture we are having. When you make sodium silicate solution, which dissolves fly ash, we get originally this kind of molecule is formed. Now, in this molecule, aluminum is substituted. Okay, 1 may be substituted, 2 may be substituted, 3 may. So, depend upon the substitution of aluminum, we get different polymers. So, if the substitution is more, we get very high temperature, ceramic materials. Only thing when and how they are substituted is a technology point. Okay. In our case, we are trying to do 1 or 2 only, and our formulation can be done at maybe at earlier temperatures of maybe ambient or maybe less than 100 degrees centigrade. But if you want to make it, temperature resistant of 1,500, then we have to incorporate more aluminum, and that technology is entirely different, and it goes to the ceramic people, where they use only temperature per reaction, and the reaction is solid to solid reactions, solid state reactions. And this is the potent cement reactions. Okay, this is how the reaction occurs, and that means there is no polymer formation at all here. Okay, so there is a difference. And now geopolymer is a word used by many people in the world in different areas of work. Only civil engineers are not using it. They are used by dentists. They are used by this clay chemist. So many people are using geopolymer for different applications, and they create their own names. So you can see these are the names available in the literature to represent the same material called inorganic material called aluminosilicates. So this is aluminosilicate, and this is amorphous. And aluminosilicates, what we know generally are zeolites. Zeolites are aluminosilicates, but their zeolites are crystalline nature. We are having amorphous. That's why it is a binder. Zeolites are not binders because they are crystalline in nature. Okay. Now, what is the Portland cement and geopolymer? They are similar. I want to say that we are not working with very new differences are required to be understood. So both are having powder material, granular material, liquid ingredient. So the same thing it is there geopolymer also, concrete also. So this powder material only will be different. Okay. But one important thing is because of polymerization, rate of strength development is. But second important is we can use the waste material available in the world. That way it becomes low carbon footprint. This is the most important aspect of the geopolymer concrete from the environmental point of view, not structural engineering point of view. Structural point of view is always there. There is no problem because the strength is developed. But these two are very important. We should always value these two rather than the strength directly. Okay. Now, And this, I want to, people may ask, what is its other properties? It has got resistance, acid resistance, temperature resistance, fire resistance, protection to steel. These have been proved by our work actually, as well as ACRC, and also by many other people in the world and also in India. So there is no doubt about these parameters. Though I am not presenting the data here, but it is already well known. So it is definitely a durable material. Only thing we should know that chemical reaction studies are still going on, and so that's why, not only that, it is not a factory made product. I mean, polymer is not a factory made as it happens in cement. Cement, everything is done in factory, only to simply add water. That kind of technology is under development in the world, and we hope one day we'll get some powder from the factory, and when we add water, it becomes our geopolymer. That formulation is still under development. Okay, that's why we should that cement is highly well-made material in the plant. So it is very, very simple to use a potent cement. That means any person, he can go to the shop and buy a bag of cement and start using it without bothering what is the reaction occurring. But geopolymer should not be like that. It is not a factory made. Only trained people, knowledgeable people should use it. Nothing wrong in that. Knowledgeable people, even potent cement also should be used. Okay, so we can see here powder ingredients. Instead of cement, we are using these two materials. And the aggregates are the fillers. There is no difference. And only in the water we are using sodium silicate solution. When I say sodium silicate solution, it doesn't mean sodium silicate solution and sodium hydroxide are separate. They are all same. When sodium hydroxide added to the market available sodium silicate solution, only its property changes. That means sodium silicate available from the market remains same technically when you add sodium hydroxide also. So when you read the paper on sodium silicate and sodium hydroxide, the final product is not anything new. It is but the only sodium silicate solution only. Okay. So at a mixer machine, there is no difference. Only thing I want to make one point clear here, that mixer machines, we are using drum mixers and things like that. Probably we should go for a better mixer where a small amount of liquid will be able to fluidify the mixture. So this is very much required, especially in geopolymer concrete also, so that we can use less of the chemical, which is the most costliest portion of the geopolymer concrete. Okay, and the molds are not different, and compaction is also not different. The only thing we should remember that we are not able to have yet admixture for this purpose. That is self-cure, self-compacting, and like that, changing on the site workability, setting time changes on the site, which is possible in Portland cement is not possible here. That means whatever we have done earlier developmental stage, whatever mixes we have used, same mix has to be used on the site without much changes. Okay, the changes is possible, but not so much as in Portland cement. That's all. And demolding time is not different, but it can be thought as a better also, because Portland cement can also be demolded within 1 day. Here also it can be, some Portland cement are able to be demolded within 4 hours. Same time can have been geopolymer. So on the whole, we can say demolding time is not much different, provided our formulation is correct. Otherwise, the original formulation was requiring 24 hours of keeping in the mold, then putting into the oven, then only demolding was possible. Now the present work, what we have done and many others are doing, that handicap is removed. Okay, and curing is most different here. So we don't require water for curing at all. We want only air curing. So whatever chemicals are present inside, they will undergo chemical reaction, start the binding action. So these are more different. That's why curing operation is so simple. Once you put it properly in the mold, then curing is started. So no separate action of curing regime is required, or curing operations are required. That saves a lot of labor and the cost involved with that. And the curing is not done in ordinary concrete. There are a lot of problems will occur, because people may not cure it with water properly. Then we'll have to undurable concrete. Such thing will never happen here, because it is simple air curing or self curing. Strength development is usually, as I told earlier, it can be made both similar, but geopolymer concrete generally they tend to be faster because of the polymerization rate. Okay, polymerization can start and self acceleration, and it will generally it will develop faster strength. Okay, that's the only thing. And grade is no problem at all, as I said. So M10 to M200, anything, any grade is possible. Okay, and the cost, as I told, it depends upon the application and the grade of the concrete, and generally with reference to the Portland cement cost, it can be either cheaper or a little bit costlier, but not very costly. Yeah, so our work showed that it may be 10 to 20% costly in some rare cases. Sometimes it is almost same. In some other cases, it is even 5% cheaper also. So cost is not a very big parameter here. Only technology of utility has to be done properly. And bond is very important for civil engineers, because without steel we cannot make the concrete building. So that also has been studied very thoroughly. And now also going on with our PhD scholar with me, Mr. Gopalan, we try to find out why the bond strength of the geopolymer concrete is more with steel. We try to find out the reason for that. For that, he has connected to chemical engineers and chemistry, and also made specially made surfaces of the rods and found out the bond strength. And surface resistance is required for our concrete, and it has been proved to be well. There's no problem. And chloride diffusion is very important, because steel gets corroded only because of chloride, nothing else. The steel will be protected for hundreds and thousands of years in concrete without any deterioration if there is no chloride ions. That means the chloride diffusion is most important, and we find that it is almost similar to ordinary concrete or even better also. So if you make it less porous, and definitely it will become chloride diffusion resistance and less, and we'll get the corrosion resistance properties. There is no problem at all. And this I'm telling this not from the readings, but actually we got the data on every one of them. Okay, and after knowing the strength and the bond and other behavior, what is the nature of the concrete? In terms of beam, slab, column, shells, all have been made and studied, and it is not different from ordinary concrete. So ordinary concrete theories can be applied to this concrete also, and we get the more conservative test data. Okay, and these two are really very good because they are superior to ordinary concrete. And temperature resistance, if it is made properly, we can get even temperatures of 800 degrees centigrade also. Okay, and definitely every geopolymer concrete is not ideal for the resistance. It depends upon the formulation. Whereas the Portland cement, it simply go away at 300 degrees centigrade. It cannot take much load, and deterioration of strength occurs after 300. By 500 to 600, it's almost strength is gone. Whereas in geopolymer concrete, by proper formulation, we can reach up to, we have got results up to 800 and above for some formulations. Acid resistance, I told you, thermal conductivity and lineage, these have been also studied at LCRC and SRMNT, and they are also comfortable with reference to ordinary concrete. Okay, that means we are able to get ordinary geopolymer concrete similar to ordinary concrete. Even when you want to make lightweight concrete, you can add whatever you do with ordinary concrete can be done with here also. That means lightweight concrete with a fly ash aggregate, which are actually lighter in weight. And when you want to increase ductility, energy absorption for some purposes like earthquake resistance and fatigue resistance, we can add fibers of different nature. That is also possible with geopolymer concrete also. And these results are also available. Only thing which is not much available is pre-stressing aspect. So there is a lot of things to be done. Even though some work has been done and results are available, but not much. But I think this is the area where people start working. But unfortunately, in India, pre-stressing operations are not studied actually in the laboratory in most of the colleges. So all engineering colleges should compulsorily buy the pre-stressing operations equipment and start working on the pre-stressing aspect of the concrete, so that when the people also, when the students come out, they are ready to know what is pre-stressing, because most of the constructions are now happening are with pre-stressed concrete. but pre-stressing itself is not done in many colleges. So I request all the academic people and professional people to start discussing this point and try to provide the pre-stressing facility in the colleges. Okay. And sometimes we want very lightweight concretes and aerated concrete we are having. Same thing can be done with the geopolymer also. Okay. People are using nanoparticles to improve the fantastically the properties of concrete. It is already well known. Same thing has been tried in our geopolymer also. It has worked well. Okay. And ceramic property particles are added, zirconium oxide and things like that, to improve the temperature resistance. They are called ceramic admixtures. It has worked in Portland cement and it will work in geopolymer concrete also. Okay. And this is the most important application. A special application for safe disposal of nuclear waste and hazardous waste. These have been studied long for the Portland cement concrete, and the recent results of geopolymer concrete show that it is far better than ordinary concrete in such dangerous treatment of the effluents outputs. So geopolymer, there is no doubt that a structural grade concrete material. And this carbon footprint is very low. There is no doubt on that. The calculations will show. And definitely it has got a service life longer because I told you all the durability properties are better than ordinary concrete. Okay. And this is the person, Readymix, actually, and he is doing work on the bond strength, and she is a professor from chemistry department, worked within our group, and that's why we are able to understand the science side of it properly. And these are other Indians who came to that one. Every year he conducts a workshop for the people, and more than 300 people attend. And in 2015 I attended, and this is a person who is and I went to China. On way back, I went to actually Malaysia. He's another big man. Though he looks younger, he is in Unimap, so at Perlis, and his publications are phenomenal in geopolymer concrete. Not much on the civil engineers work. Okay, even though they talk, lot of other people have worked, geologists and chemistry, physics. So many people have worked, and this is a really a very good laboratory there. And when I went there, actually it was headed by Vice Chancellor, who had done a PhD with our NML director, Kanamauka. So that's why he was having very much more attention to me. He gave because I came from CSIR. And later on, he called us to, this person called us to Vietnam for a geopolymer Asian conference. We made our presentations. And all of these three, another, this is 2015. Later on in 2017, later on, Gopalan himself went and made a special presentations on another international conference. And as I told you, we don't talk about the concrete only, the GGBs and fly ash, geopolymer. And this is a person who is having more than 20 years of work on the clay chemistry. He's a United Nations expert. And he produced statues like any other artist. And by using geopolymer, but this is a completely chemistry oriented, and they don't talk about strength. They talk about the formulations, so that we get any shape, any color, any size. Okay, and this is another great man, Sanjayan from Australia. He had done all the work on concrete so much. And after that, World Trade Center, collapse, fire resistance, he has studied a lot. And later on, he studied in geopolymer. He is the person who started working on 3D printing of geopolymers. And he came to our laboratory. And this is another most greatest person in geopolymer is Provis. And actually, Provis and David are fighting each other in kind of science. But he's a very, very brilliant scientist who worked on the material science side of it. And it will help us to understand what is a geopolymer concrete very well. He is in UK, University of Sheffield. And these are my colleagues in SRM University, where we did a lot of work. She is from chemistry department who did PhD, and these two were the who built the geopolymer or Center for Advanced Concrete is Mr. Dinesh. Now he has moved to Laticrete in Hyderabad, and he is continuing in Sundar Rajan. Bhaskar Sundaraj is continuing in SRM University. And we had a lot of times a lot of visitors coming, and lot of people also used to visit us. And these are all PhD scholars in different departments in civil engineering as well as chemical engineering, and including let us say the aeronautical engineering. This was a group people who worked in the geopolymer in SRM community. We hope we'll have a similar team working in Karnataka in some very good college, where they will not talk about the cost, they will talk about let us do something new. So if anybody is coming forward, definitely I can give my contribution. Okay, and actually he the man, D.V. Rangan, who was a professor in Institute of Science, who made geopolymer work so much in Australia. It inspired many people in India, and he came and blessed us, and also he congratulated us for doing the geopolymer work in with room temperature curing. And he is a professor from IIT, who was my professor 2 times in IIT, Professor Ganeshan, TP Ganeshan, who built the SRM unity. He called me to SRM unity and made me to head the lab, open the lab, head the lab, no teaching. So that it was like as a SCRC I am working, and anytime I could go out of the university, meet anybody, anytime, anywhere, which is not possible with any teachers. And so this is a man who gave us actually this MS Jain, and this is Ramani, who gave us really the sodium silicate properly. Who are working in Indian scenario, many people don't know what is the sodium silicate they are buying, because dealers don't know. So I also faced the problem in the beginning, but when I came in contact with these two people, there's a Kiran Global Chemicals, it was very easy, and we got the correct sodium silicate, defined sodium silicate. And these are all other people in the civil engineering department, chemistry department, who helped us to work on the geopolymer very much. And actually, this is Dr. Jagdish in Karnataka, and we created this chemical in a factory owned by this Prabhakar in Madurai. And so every civil engineer who wants to work on geopolymer need not talk about sodium silicate, sodium hydroxide. Simply you say, I will buy the liquid from this person and start using it. This is based on one of the formulations we have made, which has been successfully used in CRC as well as in SRM, and which has also developed a lot of PhD programs also. Now engineers can start using it, make their own formulations, geopolymer formulation, because we need not bother with the word called molarity, molar ratio. Buy this liquid and you make their own proportions for any purpose. And this liquid was released in a conference in Madurai under Association of Consulting Civil Engineers, and Jagdish is one of the leading personality in concrete technology and repair and rehabilitation in Karnataka. And we were both actually, he was doing PhD, I was doing my MS in IIT. I got a high regard for him. And he supported the good concrete technology in the country so much through his actually work in Association of Consulting Civil Engineers and Indian Concrete Institute. Okay, so just I wanted to mention the point here. So he is the man who is producing the chemical. Okay, so now coming to our pyramids. Okay, now as I told you, geopolymer is not Portland cement. Geopolymer is a polymerized material. It is having aluminosilicate system. So anything having aluminosilicate system, we can take it as a new material for Indian from present consideration, but it is as old as pyramid. Okay, so people have to work on the different minerals. Now we are working only with fly ash in GGBS, whereas in Egypt they use the local materials and try to produce the new binder at that time. And now David Rhodes proved that it is nothing but aluminosilicate type of binder. Okay, now this is a very famous pyramid, in Giza. A lot of people have visited and studied it. And limestone is not that limestone directly. Limestone becomes a part of the aggregate of the geopolymer concrete. Okay, and 5 million blocks are used. And the 5 million blocks, when they are using the surrounding area of the limestone deposits have not changed much. Okay, And so there's and also they proved that many studies have shown that this is not a carved stones. It is actually stone made, cast with agglomerated limestone concrete. See, the word is important, is agglomerated. Limestone particles are present, which is calcium carbonate type, but they were remade into stone. They took the limestone like particles and bound them together using some system thinking, and that is the agglomeration. What we call also present concrete is also we call composite concrete. It is also similarly the word they are using is agglomerated. Okay, limestone is broken. People think that limestone is broken. Again, they made into stone. Okay, that also we can think. Otherwise, some limestones were very fragile there, and they automatically become different aggregates, and they connected them and made the binder. Okay, and some are weighing, stones are more than 30 ton, as Kaushik was mentioning, and it is impossible to imagine how could they handle this such a large sizes and bring to the place where using the. So that's why this technology of making on the site is very clearly to be decided and to be understood, so that we can move forward in the present days also. Okay, and Egyptian pyramids is Giza, and many studies have showed that they are actually man-made stones and look exactly like natural rocks, because they use the available materials surrounding there, and they bind them using their knowledge of the binding action. And naturally, but the binding action is so good, and binding action binder itself is so small, the whole thing looked like an ordinary rock only. Okay, so and they were made in the site. And this is one more great pyramid at this place. The 2.5 million blocks were used, and most weighing 2 tons. And if they have to use 60 people to haul this. If they are, there is all estimation made, and some way up to 70 tons. How could they take it to 40-meter high? And 2,000 people were required to remove, haul one block. So such heavy, human resources cannot be made available at a point. And there is some other discussion going on where on the site the space can handle only about 2,000 people, 2,300 people only, and that is also recorded in some of the literature of Egypt. So when only 2,000 or 1,500 people are present in a site, how can they handle such big stones? That means it was not handled; it was made in situ. That is what people are trying to tell. And this is a great man, Farah. Actually, he had a service of 20 years away. Okay, and if it is a stone, they have to handle minimum 400 blocks per day. Okay, and wheels were not available at the time. Pulleys were not available. And what about the stones? Stones are not very good. Limestones available are hard, and when they want to make it to some shape, it will split, and we cannot cut to the proper requirement. So definitely, and when they cut it and make it to shape, there will be 5 million tons of blocks produced required, and they will correspondingly millions of broken blocks and fragments are required to be actually made available as a waste material. And now there is no place where such blocks are available in the I think in the surrounding areas. That means they were not made from the original blocks. Okay, cutting. The same thing is said about Ajanta Ellora construction also, where especially Ellora temple, Kailash temple, nobody knew how the technology, what technology was used, because that is a top-down approach, and so many stones are removed perfectly. And where are those taken out stones? Nobody knows. Okay, surrounding areas. So at that time, technology was so different and so environment friendly. We are not aware yet. Okay. So anyhow, coming to this pyramid here, the joints are only 2 mm wide. And this stone mold cannot be made, in if the stones are made in the handmade cut stones, joints will be always, not perfect, and there will be differences. Okay, and the blocks are so perfect, they meet at a point in the top. So that is not possible with ordinary. It is very tough job with so much of size and weight, and it is possible only if it is made in a castable way. So that every block is made to the mathematically calculated size and shape, and we can use it. And these are the earlier what I told was the generally what we can read in the as a summary of the literature. Okay, available in parameter. But if you come to the actually people's names and things like that, this Barasom at Drexel University, he found that there were two types of actually stones available in the pyramids. One is from the quarries and from the man-made. And he proved that these two materials have different chemistry. Even though they are both are aluminum silicate and similar chemical compound in terms of oxide, but there are other ways of looking at it chemistry wise, and they are different. And he proved that these quarry surrounding is having a different chemistry than the chemistry of the lateral limestone blocks made in the used in the pyramids. And Professor Hogg is another scientist, professor there. He compared pyramid and surrounding quarries. And this person used X-rays and plasma torch and electron microscopy, and he wanted to tell that the stones are not natural type; they must have been artificially made, and we use the word concrete. So he felt that he proved that they are all man-made and casted. Okay, they are cast on the site. So this was proved by X-rays and the plasma torch and electron microscopy. There are, it seems, tools available to differentiate between man-made concrete-like thing and quarries. Okay, but I want to make one point clear here that ordinary concrete is also a stone, but we use a lot of cement here. The binding material is so much, and we are having that sand and thing. When you open it, it will be definitely feel it is not looking like stone. So the technology available at present time is different from the time at that time they made the concrete. So that I wanted to bring to your notice. Okay. Now these people, they found that limestone, what is available surrounding, dissolves in large Nile-fed pools. Actually, Nile is a river, but in any water, the limestone dissolves. Not in the sense the stone itself. The particles are all having some binders, and the binder will dissolve. Okay, and the binder dissolves, and a lot of slurry is formed there. Okay, now the slurry can be used as a binder by mixing with lime and fireplace ash. So when they use some burning activities for so many purposes in their life, the whatever ash is available, that ash was used to. There is nothing but a fly ash, we can say, present day term, which is unburnable material is only lime. Unburnable material is silicon and aluminum. That's why the ash will contain mainly silicon and aluminum, and this was mixed there, and salt. The salt is to generate the some kind of a pH level, alkalinity level, and this is also naturally available salt. You can see in the picture. Okay, and this was actually made. That's what they try to give theory behind this, based on the actually studies they have made in the inscriptions on the site there, and which debuted fundamentally a fantastic work. And when the slurry is mixed with this and the water is allowed to evaporate, what we get is the clay-like material, and this material becomes a binder now. So the chemical reaction has taken place when all are mixed and allowed to evaporate. This may take few days to few months, and that available material final product is called a clay-like wet mix. And this wet mix can be put into any mold and actually compacted, and that starts slowly setting, and it becomes a perfect stone. there's no much difference between the natural stone and this. So the time involved here is very, very large to get the final rock type, it's a blocks, okay, concretes. And at Giza, he found, these two people again, they have, I already have mentioned that they have done a lot of work, and they found scientific evidence to show that parts of great parts of Giza used an early concrete. That means, at that time they didn't use the word concrete, but we can say concrete is a material which has got a lot of filler materials of different particle sizes and bound by a properly planned binder. Present we are using Portland cement. Sometimes we can use epoxies and polyester resin also. Okay, and he found that that this must have been done. Otherwise, such construction would not have happened. That is more than that. He wanted to prove that that there is a concrete and it is not exactly like a natural stone. Okay, and by the theory they proved that they were not at all cut stones. So they were actually the only thing that because it is looking so natural and so good and so perfect, they felt that nanotechnology was also utilized indirectly there. As we do in India also, we are having Tipu Sultan's, the Tipu sword, and also we are having Qutub Minar, and so many things we are having where nanotechnology has been proved to be used. Only thing they didn't use the word nano, they did it purposely, and they observed it and they did the work. So because of the nano nature of the particles involved, we get the extraordinarily different property of the material we are having in hand. And such thinking was made in the pyramids also. They use proper materials, nano level, and whatever they wanted, they could get. And this another material scientist in Belgium, and he observed that there are holes and there is a bottom and top. There is a difference in the density. So that happens in cast concretes. Doesn't happen in natural stone. Natural stone, everything is homogeneous, but in ordinary concrete, we can clearly find out the top is having little bit of bubbles because the air is passing through, which was which was entrapped during the mixing, and this what we can look at the slight changes in the density, and this was observed, and that it proves that it is not a natural stone. Okay. And so when they proposed this idea, then they found out that this construction using the sloped inclination for hauling and thing was completely demolished. That's thinking, because that kind of hauling required, they made the estimation about 1 lakh people were required. Okay, when they did the estimation, depend upon the weight and the distance and the speed of movement, all these things when they did, it was in one case it was requiring 1 lakh, and they found out that 1 lakh whatever volume they are having to be made to make available at pyramid point, it can be made only about 2,000 workmen, because it is only question of taking to the site and putting into the place there, or only compaction is done by ramming. So that manual work is very much less, and most of the logistic is completely removed. So this was possible to be explained by using the word called re-agglomeration, and also by understanding that it is a in situ made concrete. And I think this people can see, have a look at this YouTube, where David Woods made actually the stones in his France laboratory and sent it to different geologists in the world, and they could not certify it that it is not a natural stone. They all certified natural stone because the technology they are having is only that type only. Okay. There is a YouTube has got this point program, and so we can see he has made those building blocks using the material available in the Egypt and brought them to Egypt, France, and used in the way they were using in pyramid making, and he found that those stones are similar to what they found out in the thing. And also they also proved that why the surface is smoother, why the surface is this thing. It all depends upon the formulations. Okay. And this is another wonderful pyramid thing where when Egyptian is in Djoser, he is a great king. People were not using much stones earlier. Only after this, only the stone used pyramids came out much in the Egyptian area, in that area. That means, because he proved that actually he is a great scientist. And when the inscription said that there is a person called Kum, who is similar to God, who comes and tells to this king in dream how to make the concrete like material, stone like material, without actually spoiling the nature around. That is a god, So he told how to make the stone like structure, the same strength as stone, so that but at the same time it is not disturbing the environment outside surrounding. And with the facility and the people and the knowledge available and the resources available, it should be made, so that whatever they are dreaming of building a big temples and statues can be made. So this is available in the actually David studied all this literature thoroughly, okay, and deciphered them, and he proved that these are all accounted there in the literature itself. How to make the aggregates and concretes. Okay, we can read this, and we can know that this is not just like it has come out. It is the thinking of the people who felt that some materials can be mixed together and allowed it to become hardened, and hardened material is very strong enough to sustain for thousands of years, and that we call it as concrete. So this knowledge was slowly built with different contributions, and what are the sources of materials and how to use them, all are told in their language in a different way. Okay, it is not our type of paper writing, it is their way of telling how that is made. Okay, and but the most important thing is David found that there is a geological glue. The glue is actually making the difference. Okay, and this glue will agglomerate the mineral particles. Mineral means here we are talking about limestone. So product is rock looking perfectly natural, extremely solid limestone, similar to certain types of occurring limestone. Because the basic material also use limestone particles only as a filler material, and the binder was also made from the available surrounding minerals and the material which has gone out of fragile limestone, which is the clay material. And when he made the rock, it was similar to the limestone naturally available. Okay, and but when he said this to the different people, and the geologist agreed that it is a stone only, natural stone, because the geologist having their own way of defining a material, and using the tools, they could define it as a rock, natural rock. Okay, but only thing, they could not, geologists don't look at the very minute points, and their observations on the binder portion are very poor, I mean less. So they concentrate more on the bigger particles. That's why they lost the actually thinking of the binder, which was the contribution from W. And he created the binder using the natural material, and mostly it is a clay also. Okay, and he understood all these minerals. Okay, and what is the chemical composition of the minerals available there, and is recorded in the actually inscription there in the Egyptian area. And he read all that, and he created his own theory of making this glue, and actually, as I told you, he produced that. And Only thing, German scientists already told that this 90 to 100% of blocks came from the soft and argillaceous limestone layer located in the body. That means this kind of limestone had a softer argillaceous means the clay-like material, which gets dissolved in the dislodged from the rock-like material in the water. That's what the dream was telling him, that king, and that argillaceous clay-like material becomes a better if it is proper. So present way they call beneficiation of foundation clay and all the things they talk. Clay is strengthened by lime and cement, like that they are talking. Similar way, things were there at that time, and he found out that the clay is available already in that area, and that can be utilized. Okay, so crumbling limestone, which was not useful for making the actually blocks. In the sense, they cannot make cut into required size of blocks because their limestones were crumbling type, soft, because they are having a lot of clay minerals, and the clay minerals themselves, it was itself getting dissolved when it is put in the water. So that's what it is told in the by observation and in the literature available at that time with them. And that's why they didn't use these limestones actually directly. They used only the soft limestones, which are plenty available there, and which gets dislodged into small pieces when put into water, and that water itself becomes a slurry, and the slurry and added with silica and alumina containing material like ash and lime, it will become a polymeric, geopolymeric material. That's what proves it is proved it by the experimentation. Okay, so he found that he's a Lal Gauri, K. Lal Gauri. Actually, we had a chance to work with him in 1978-79 in SCRC. He's the greatest geologist who worked on the this our Taj Mahal also. He's Indian, but he was a UN expert. He came to SCRC, and we spent, and at that time we went to Mahabalpuram and tried to study how to repair the monuments of the stone without affecting the future durability. So at that time we were working on polymer concretes, and he had done a lot of work on he is a geologist, and so he proved that this limestone, some of the limestone is having clay-like material sensitive to water and too fragile to be hewn stone. I mean, that limestone available at some points there, it cannot be cut into a perfect block with high strength. So while doing it, it will crumble. That's why, but it has got other property like a clay-like material, which can be made into a binder. Okay, and once that is available, that crumbled particles can be made to agglomerate again, and by using proper binder. That's what Gauri has also proposed and thought that it must have been like that, but it was practically done by David and others. And what he found was the David, it is not necessary to crush the limestone nearby, because it's very difficult to crush a hard limestone into proper shape. It requires a lot of effort and the time. And but some of the limestone available disintegrate easily with Nile water. Nile, I don't know why you use the word Nile water, but any water. And so, as I told earlier, it becomes a mud, and that mud, he proved that they added some other material like hydrated alumina, copper silicate, Egyptian nitrogen salt, that is nothing but sodium carbonate, lime coming from plants and wood ashes. All these things were studied, added to that slurry, and it started becoming a binder. And he studied this from the literature available on the inscription there, the David Woods. And he proved that that mixture can be taken in baskets and poured into the molds. Molds are made out of wood, stone, and crushed brick, and directly on the building site and packed. Then after some reactions, it will become, actually he called it as a geochemical reactions, and it will become they will retain the form of the molds, and they will remain like that. And he had a system where he could make 90 to 95% of the limestone aggregates, but filled with only 5 to 10% of geological glue. So this he discovered and he used in his making and proved. And a geological glue, though artificial, it was taken as impurity by the geologist. Why geologists said pyramid as stones? Because they didn't understand the presence of geological glue, okay, and they took it as an impurity in the stone. But that's why they didn't study much. But whereas these modern scientists who are not really geologists, chemicals and chemical engineers, they use these materials, these modern equipments to prove that there is a difference between natural stone and artificial stone, and the difference comes out of this modern equipment like NMR spectroscopy or FTR, XRD, XRF, XPS, so many things. It will show the actually the structure of the microstructure of the material, and what are the elements, how the elements are connected to each other, elements, how they are connected. All this can be studied by this modern equipment in different ways. Okay, and that is the strength of these modern scientists like David Oates and others, and they try to show that pyramids must have been only man-made, not actually natural stones, because they proved that natural stones output will be different and when these equipments are used to characterize them. Okay, so kymatic clay, that's what you use our clay brick making. Okay, and caustic soda is nothing but sodium hydroxide to create the aluminum refined condition, and caustic soda is coming from that sodium carbonate, which is a mineral. Okay, so caustic soda, he proved that sodium hydroxide can be produced from the sodium carbonate and lime. There is a methodology he proved, and he has used it. So, but now thing is very important is how they should be combined. When they are combined here, NaOH is combined, NaOH is combined. Say we produce one hydrosodalite is a mineral, and we get here one more limestone here. The same local ingredients form two types of actually material. One is a mineral which is not a binder type and not very strong, and it is like a stone, but it is not strong. Whereas here no limestone is made. That means clay plus natri sodium carbonate and lime, it produces these two kinds of what geologists called it as minerals. Okay, and these two are nothing but natural stones. So geologists, when this reaction produces some material, and they try to find out what are the minerals available, they identify these two materials and say it is a natural stone. And so geosynthesis was the actually work of David Oates to show that geological materials were used for making the binder. And so what we can say is pyramids are made out of concrete. If you say earlier people think it is carved stone and hauled to the site of pyramid, hosted and placed in exact position. This was the original thinking of many people. But the question, this raised many questions, like as Kaushik was mentioning in the beginning, 20 years his reign was there, one person, and he built one big pyramid, and that pyramid had so much of building blocks, 2.2 million ton, and the at the height of they were taken to the site some, okay, and 2 to 70 ton weighing, and no wheel was available. Okay, and each block required 2,000 people to haul, which is impossible to produce such a manpower on the site. So, and if they do it, they could do it only 400,000 people is employed. They do only 400 blocks per day. Then the whole 20 years they have to go on doing it. It is, I don't think any construction would have occurred for 20 years of this person's reign. Okay, So that's why it was felt that this kind of thinking is not possible. Use of natural stone as a material in the pyramid, it must have been other technology. Okay, so limestones, as I already told, it was very extremely hard material. So it cannot be cut by copper saw was available at that time. They had only copper saw, and it is so soft it cannot cut limestone properly to the shape and the smoothness. Okay, so if we start doing it with tools, it will start getting critical, and lot of fragments will be coming out. And as I told earlier, these fragments are not available in plenty of surrounding areas. That means they have not done the cutting action. Okay, and perfect joints, as I told earlier, 2 mm wide, which is not possible to produce in an ordinary stone. It will be always having very different thicknesses, and 2 mm is very small amount. That can happen only in the molded status. Okay, so the bald blocks can be made to the exact calculated lengths set in patterns without any vertical joints. Okay, so David Woods proved that they were not called, they were cast in concrete, and geochemical reactions have occurred. And he proved that he went to the site and studied that soft lime in the Giza area, and he told that water will make the slurry, and slurry added with salt and other materials available in the community to make a binder-like material, which becomes a binder after evaporation and the chemical reactions, and that itself binder is used later on to produce the agglomerated concrete. That is called wet concrete, he calls. Okay, so the wet concrete is taken to the site and put in the molds. Okay, and he has given so many references, David Woods, these references to show that limestone, whatever the limestone was made artificially, was looking like a natural stone, but it is not a natural stone, it's artificial stone. So all this literature is available for any person to go through to prove that natural stone are not material of construction. So you can see here, X-ray diffraction, modern DTA, all these modern equipments are used, okay, to prove that. And so we can say that man-made geopolymers were used, cast blocks like modern concretes by they were done, and nearby minerals and were used, and natural stone like concrete blocks and high durable cast. Okay, and this is not pyramid in Egyptian area, and similar knowledge is available all over the world by different communities. So this is at Bosnia, and the studies made showed that the high quality man-made material was used there, and the blocks had similar inert material with a binder similar to ancient Roman concrete. They studied that using chemical and diffractory analysis, and confirmed that Bosnian pyramids, which are a few thousand year old, some of them are much older than pyramid. The Egypt pyramid, it was nothing but it was a man-made material study. And so this already I have discussed that he studied Bosnian also, and he felt similar way as he did in Egypt. Okay, and this is another Bosnian pyramid. When they studied, it is 220-meter height, much taller than our Egyptian pyramids. Okay, carbon dating told them to be more than 25,000 years old. Okay, now analysis, material analysis made that they were man-made concrete. It is not natural concrete at all. By this great scientist of anthropology and archaeology in the Bosnia Herzegovina, the country there. Okay, and one thing is very important is I want to bring to notice of our friends here is that pyramid was not meant for only construction. It was meant for actually energy production in the world. And so the shape is such that it creates a lot of energy, and the energy can be actually collected. That's what they proved here. So in this pyramid, it was they found that in electromagnetic energy, beam was coming up from the top of the pyramid. Okay, because of the shape, and they found out what is its frequency, how much distance, all these things they calculated. And because of this, energy level of the pyramid being different, and also they should, because they have to orient it towards the Earth's magnetic field, they did it perfectly. And that means, environmental energy environment inside the pyramid and surrounding the pyramid was so different. And they studied human physiology and emotional status of the people inside. It was found to be very good, because there was no negative ions of the present day atmosphere available in this pyramid and surrounding areas. That means, pyramids were supposed to be highly thought over scientific, we can say, structures, not only for building the structures for, let us say, for things and things like that. It was meant for even producing electromagnetic energy also. This study was made for both. And so I just wanted to notice that, geopolymer concrete is a material which is having a binder in the form of aluminosilicate, which is amorphous in nature, which is not amorphous when it is zeolite is made. Zeolites are perfect minerals with, mineralogy of aluminosilicate, but crystalline nature, and they got different properties. They got, hazardous gas absorption, and so many things are there. But we are not interested in those applications of aluminosilicate. We are interested in using it as a agglomeration. Making a agglomerated concrete. Inert materials are bound together, and that binder is made. So, like Portland cement, this geopolymeric material, which is inorganic polymeric nature, can be made. And present day people are working with only fly ash and GCPS, to some extent metakaolin. Now it is the time to get away from these two and start working with other materials like iron ore waste, manganese ore waste. So many wastes are available in the country because of the mining action, and they do contain this aluminum and silica. And how they have to be activated to get the or polymeric action, polymeric formation, and that means, a lot of material science is involved. So a lot of material science, so that people from physics, chemistry, chemical engineering, people have to come together of different backgrounds and come together and produce these new materials, and then civil engineers start using it. So civil engineers are involved, should be involved to understand how they are producing and what we want from them, and we can give our requirement of the strength and the workability and all those things. They can work on that and come back to us. So there is a teamwork involved. So I request all the engineering colleges to compulsorily involve chemistry and physics department to work in geopolymer in their own way. It is not easy for them, and not for the civil engineers also. But we can start working on that, and probably I can help them how to bring physics and chemistry people into our work, civil engineers work, because usually they don't come together at all because thinkings are different. But we can make them to understand, and that is experiment to some extent was successful in SRM, which I could not do in SERC, but doesn't mean that engineers wait for them. We produce without them also, but it will be more development will occur if they also coming. That's what ordinary concrete has become. A lot of chemistry people work and they produce excellent admixtures. That work is also required to be done in geopolymer concrete, where with less of the liquid, how can I increase the workability? Okay, all those things are to be done. So there is still a lot of work to be done in geopolymer concrete, and people should work on the new side of the geopolymer concrete, not whatever is being done, whatever is done earlier. You should not think about only writing for the papers and the thesis making. That should go on. At least some people should try to produce new ideas, new thinking, so that we go beyond this fly ash and GGVS and beyond this sodium silicate and sodium hydroxide, and think about different activating systems. So that's what I say now, and I'll be very happy to receive any queries. But if the queries are not answered now, or if there is no time much available, also doesn't matter. And queries, our organizers will collect them, and we will try to find out the answer for them. And if the answer not available, that becomes research points for many of the people who are in academic areas. Thank you very much, friends. And I hope I was not too much, chemistry or physics or something like that. I wanted to make an overall picture, because I got some details about how the, this XRD and the FTIR and the SEM were made to look different from artificial, but I didn't want to put only science here. I want to take a general view and engineer's view. That's why I made it a little bit more simpler, and only concepts and ideas I was presenting, which was done wonderfully in a summary way in the beginning by our friend Kaushik. But I want to make here one point clear. What is the role of the binder? I wanted to make one point clear here, because David went to France and we found extremely beautiful and different shaped, ceramic home utility items and things like that, even decorative items. And you felt that it could not have been made from the usual so-called marble and things like that. It should have been site made, that means mold made. So similarly, that is the importance of the molding and the glue you use for that. And just I wanted to bring to your notice that the peanut butter from the groundnut, when they make it, groundnut is not added anything. Groundnut is put in, it seems I saw that YouTube also, groundnut is put into a mixer machine, and it is only ground mixer, it is simply operated at different what you call speeds and things like that. Finally we get a paste. How can a solid material doesn't seem to have any liquid in that, gets a paste, and that becomes a butter? So that is the advantage of putting all the particles into proper size and get it surrounded by a proper binder. So here that oil is like a binder, and all these powdery materials get bound properly in a natural way in a nature, and we get the solid these groundnuts. But we can bring it back, we can make a paste out of it using the liquid available in different ways by giving energy to it. And I think the particles are broken down to nano level, and the oil becomes a binder which is very thin is required. Atom and molecules are so small in number, a small amount of oil or liquid can spread over large areas, and that becomes a binder between the particles. And that is the way ultra high performance concrete is made in the present world also. So the binder is distributed properly and made to react properly without having chance to get any porosities, and we get the ultra high performance concrete. So this I want to bring to your notice. That means knowledge was available with those bright brains in those areas, and they produced those wonderful structures, which is there in India also. If you go to Halebed, Belur, and all these old temples, how could they make that very, very intricate the designs and the shapes and the sizes? Somebody, I was trying to find out the reason for that. Maybe they are having some idea where they can convert the stone into a liquid and bring it to that shape. Like they do in the glass blowing people, when they make glass atoms, they take the fragile, you can say brittle glass into their hand and apply this flame, and it melts. During the melting stage, they create shapes to it fantastically. So that is the skill of the person as well as the material handling properly. So these are the things probably we have to start learning and thinking. Thank you very much.
Thank you so much, sir. Now I'll read out few of the questions received from the attendees. The first question is why the shrinkage in geopolymer concrete is less than normal concrete?
Actually, there is a controversy here. Shrinkage, some people said is more, some people said is less. Okay. Actually, what happens is in a geopolymer concrete, the chemical reaction itself produces water molecules. Actually, water molecules are absorbed or utilized in cement hydration, and here actually they are produced. And the water molecules, when they dry out, there is a shrinkage. So controversy is that some people say geopolymer concrete will shrink more, some people say less. But I find that can be studied properly, and depend upon the formulation, it can be controlled also, and that work is required. And in our work, in our chemical compositions, we didn't find any effect of the shrinkage being too much excessive in terms of any property we could get. So it is a good point, but shrinkage measurement has to be made properly, and that's what pre-testing when the work is going on. I think the study will be made. But generally, it is supposed to be less in some formulation, more also in some formulation, and as happens in ordinary concrete also, if the water content is more, if the chemical admixtures are a different type, shrinkage is actually not controlled there. And also this water drying produces some pores and shrinking of the gel structure. All those things can be controlled by proper study of the microstructure of the concrete, and the reason for that. Same thing can be applied to geopolymer also. It can be done. Thank you very much.
Thank you, sir. The next question is, our produced concrete is durable for hardly 100 years. How is that the man-made stones for pyramid, in spite of thousands of years old, are intact?
Okay. Actually, this is a wonderful question, and the reason for that is two things. In present day, concrete is never a concrete itself. It is a reinforced concrete. So we are having two materials. One is steel, another is a concrete, and their combination should be durable. That is our requirement. That means steel should be made to be present properly inside the concrete, so that steel will not get attacked by the surroundings. It naturally gives, concrete gives the support to the steel without any problem, as I was telling. So in alpine environment, steel will never corrode, but steel is in unnatural state. Natural state of steel is iron oxide. Now it will try to go to iron oxide, but if the alkalinity is high, it will not undergo chemical reaction. So as long as the alkalinity is left surrounding, there is no problem. The steel will get protected. But if the chlorides enter there, that the natural oxide formed on the steel, which does not allow further deterioration from the surrounding chemical nature, will be absent, will be made to become absent if the chlorides and enter. So if the chloride diffusion is controlled, the structures can be not 100 years, it can be 500 years. Actually, 1,000-year-old construction has been made in, I think, White temple, where this PK Mehta produces the concrete, high volume fly ash concrete. He proved that it can have 1,000-year service life. So, how the concrete is made, it is most important. The cover through the thickness of the steel is important. If they are taken care, no problem. You can example is a few millimeter control on the cover thickness, so perfectly made in a Lotus Temple, nothing has happened to the Lotus Temple. Okay, one more example in our SCRC, only 12 mm thickness water tank was made of a few thousand liters. 12 mm thickness ferrous cement, no corrosion even after 40 years. Whereas you can see the corrosion occurring in any place. So the question of how do we make the concrete? If the concrete is made in with proper cover and proper what you call porosity levels and curing and other thing, the steel cannot corrode, and reinforced concrete can become a forever material. There is no doubt in that. Only when the surrounding becomes dangerous and we are not controlling it in the concrete, it is dangerous. For example, sometimes sulfate attack will come. So if you know how to control the sulfate attack, the concrete will never corrode in that sulfate environment like that. So knowledge is available, application of that properly on the site, if it is made, there is no problem at all. Thank you very much.
Thank you, sir. The next question is, why is steel more bonded to geopolymer concrete than it does to ordinary concrete?
Okay, this is an interesting question. Actually, what happens is there is a chemical nature. No, it is a polymeric structure here. Okay, polymeric structure creates and also alkaline in nature creates some kind of different molecules at the interface. That's what our Gopalan, who is a PhD scholar, trying to find out. And he has scrap. Actually, he made a steel rod completely shining by proper actually late treatment. He got a completely shining smooth rod, and he made a geopolymer concrete around it and studied took that piece between the steel and the geopolymer concrete, studied its chemical properties, and we found that it is slightly different from surrounding areas because it is an interaction between the steel and the polymeric structure which creates a different kind of bond. Okay, actually there is no time here, but we can show that the bond is such that it is a strain hardening type. That means when the steel is being pulled out of the geopolymer concrete, suddenly it will not come out. It will slowly it will come out, and actually once the final load is reached, bond load is reached in the correct formulation. I'm talking about the word correct formulation. The steel rod will continue to hold the steel. The rate of bond strip is slightly reduced. That what happens is strain hardening type of behavior in the steel as well as the ultra high performance concrete where they put micro fibers. So that creates strain hardening. That kind of behavior is found out in this geopolymer. Probably one more day we can have a study on the what is the bond nature. Basically, what we can now understand that it is the inorganic polymer is present here. There, in ordinary steel, there is no polymeric binding; it is different binding. The chemical reaction between the two different, and the interfacial zone is different here. That's why it is slightly better. But finally, structural behavior is almost similar. There is no problem. Okay, bond is better. In some situations, it is good also. Okay, thank you very much.
Thank you, sir. The next question is, while designing a new mix, what should be considered as the main factor? Workability or less carbon emission?
Pardon, you tell me again question.
Sir, can I repeat?
Please repeat the question.
While designing a new mix, what should be considered as the main factor? Workability or less carbon emission?
No. See, our concrete is made for different purpose. We want workability or fresh concrete properties we want. Then we want it to be moldability. And we want to get this strength. These are different. Carbon property is another issue. So when we get the materials formulated for this purpose in ordinary concrete, and we get the final mix, and then we can calculate the carbon footprint. But there's a limitation and reduction of the carbon footprint in Portland cement concrete because binder is mainly the cement, and Portland cement requires a 1400 minimum temperature. That means energy requirement for production of the binder is very high. First, second, we burn the limestone, so carbon dioxide emission is compulsory there. There is no way we can avoid it. So these two are not required for these two are not eco-friendly operations for Portland cement. Only eco-friendly operations I'm telling, but not the engineering properties. They are perfect. Whereas geopolymer, we don't depend upon this Portland cement. We take the waste material like fly ash and GGBS, which are supposed to be having zero energy content because they are waste materials. And also, no doubt, we use sodium silicate solutions and things like that. It has got energy content. But when you calculate that energy content of the total mixer, definitely the total energy content carbon dioxide emission level is much less than that of the Portland cement. And our calculation by actually Mr. Gopalan and others, we have proved that 1 cubic meter of geopolymer concrete, okay, if you replace with 1 cubic meter of Portland cement, okay, it is equivalent to 100 trees. Because carbon dioxide emission, there is a calculation available in the UN to tell that how much is the carbon dioxide is used by the plant. for so many years. So that means, you know, there is a very good advantage in terms of carbon dioxide emission level of the materials used, so that our concrete per cubic meter, our concrete becomes less carbon dioxide emitted material. That's why it is more eco-friendly. So I told at the beginning, we are not talking about the cost. So this carbon food production is not related to the cost. It is related to the environmental degradation and the climatic problems. So there is no cost involved there. We should not talk in terms of cost. How much cost is required to repair the environment? It is not possible to find out at all. So only thing, you should not become double the cost of production market. That much is sure. So it may be 5% costlier, 10% costlier per cubic meter. But the advantages will overtake that. So that way it will become cheaper also in the overall run. Cost effectiveness is very high. So there is no problem with the cost. It is only per cubic meter wise, it may be slightly costly in some cases, it may be cheaper. Doesn't matter much.
Thank you, sir. Sir, the last question goes like this. Will geopolymer concrete have any additional benefit in sulfate soils, or is it the same as SRC concrete?
Okay, sulfate resistance concrete you are talking. Okay. And you know, sulfate resistance is sulfate attack occurs if there is a free lime. And the ordinary concrete produces free lime as part of the chemical reactions. And the free lime is reacted by the surrounding, sulfates, and we produce gypsum. Okay. And the gypsum creation and corresponding intergrade creation creates the problem in the durability. Now, as there is no free lime here in the geopolymer reactions, definitely its sulfate resistance is higher, because polymer structure is such that it is not much attacked by the sulfates much. Okay. First. Second is, in the ordinary concrete, there is a calcium silicate hydrate gel is formed, CSH gel. So that calcium should not be replaced by any other material. Okay. Now, if you put magnesium sulfate, magnesium ion try to replace that calcium in a time. That is called sulfate attack of the magnesium sulfate. Then if the CSA gel loses its calcium, binding action is gone. That's why it deteriorates faster, but it takes time. So, sorry for all the academic people, we should never work on the sulfate resistance of concrete for less than 2 years. At least minimum 1 year we should work, and then only report the data. We should not report the data on the sulfate resistance within 6 months, 3 months, and 9 months and 1 year. No, it will not. It only after 1 year only will some of the formulation will start giving the deterioration. So one example was, we studied the sulfate resistance of fly ash concrete. If the fly ash content is 50%, okay, up to 6 months, the strength was increasing. Sulfate attack was not occurring. After 1 year, it started reducing, because the CSA gel was less in the 50% fly ash content, and our sulfate was, magnesium was attacking that CSA gel. It takes time, there's a time, and then deterioration was very fast, because it was under a DST project, Department of Science and Technology. It was supported by CPWD, who could carry out work for 3 years. So I request all the academic people to work on the sulfate resistance for not less than 1 year, then only report the data. Otherwise, don't report the data at all. That's what my request. So sulfate resistance is very high here, generally speaking. Though no doubt some chemist people will say your aluminum structure, silicate structure may get destroyed by the sulfates ions. So you should talk about that, but no doubt it occurs. But the rate is very small as compared to ordinary concrete, where gypsum formation is a possibility of free lime. Calcium silicate hydrate gel is getting deteriorated due to the magnesium ion. But I want to bring to notice here, sodium sulfate and magnesium sulfate attacks are different nature. So if you study sulfate attack, you should mention what is the sulfate you are using. Don't take it as general sulfate attack. So sodium sulfate attack is different from magnesium sulfate. Right? The report is proper. Okay. Thank you very much.
Thank you so much, sir. That's it.
Yeah, thank you, Anjali. Let me come to the end of this particular session. Good evening, friends. We have come to the end of another very interesting topic, geopolymer used in pyramid construction, a scientific view. I thank Dr. N.P. Rajamane for delivering a lively and vibrant talk on the topic. He kept the audience glued to the webinar. Thank you, sir, for sharing and putting it in right perspective regarding the mystery surrounding the pyramid construction section, and also clear the doubts regarding the geopolymer concrete. I also thank ICI Mangalore Center Chairman, Secretary, and Treasurer, and executive team, entire executive team of Mangalore, for associating with QCrete webinar series. Once again, I thank all the participants who had spared valuable time to attend our QCrete webinar series in large numbers. And I'm Shelly Fernandez from QCrete Readymix India Private Limited, signing off till we meet again on the next interesting topic in QCrete webinar series. Thank you, sir. Thank you. Thank you, sir.
Thank you very much. Thank you all.
Thank you, Rajman sir.
Thank you.